Thus, you ask yourself the question, am what I'm saying right now is a lie? Hey, I'm live! Hey. So, I don't know if there's anybody actually in the chat yet. It doesn't say if there is or not, but I am going to begin regardless. Again, just trying to make sure everything is set up the way that it should. Come on, you. All right. Let's talk Hi-Ho Cheerio and how this relates to what we're doing with random simulation. The game of Hi-Ho Cheerio, as we briefly discussed, is in regards to cherries. You are attempting to get all 10 cherries into your bucket. And if you successfully get all 10 cherries into your bucket, then you get to yell Hi-Ho Cheerio in a bombastic way. But there are certain pitfalls and stumbling blocks along the way. See, the spinner has 7 equal spaces, and this is where the random selection comes into play. If I were to spin that, depending on what it landed on, I would have to either do something or, unfortunately, in this case, I do nothing. I landed on the space for spilling my bucket. I already have nothing in my bucket, so I don't do a thing. I move on to the next person's turn. You can play with 2 to 4 people. If you land on a 1, 2, 3, or 4, you take that many cherries off your tree and you put it into your bucket. Seems simple enough. If you land on a bird or a dog, then, well, you lose 2 cherries. 2 cherries come out of your bucket and go back up on the tree for some reason. And then if you land on the spilling of the bucket, you lose everything in your bucket and it goes back up onto the tree. The kid who is like the funniest one in this whole thing, this kid right here in the yellow shirt, he's just like, I don't even know what he's doing exactly, but in every panel, he's just hilarious. But anyway, I digress. Let me play a game. Now, in the past, I would have students actually play the game for me against each other, but you're supposed to be staying away from each other for some reason. I don't know why, but I'm going to play it anyway. Let's just see what happens. And I'm going to have fun by myself. I got 2 cherries right here. Yay, go Team Yellow. I don't know. You pick a team. Green. Oh, I got a 4. I got a 4. 1, 2, 3, 4. There we go. Team Yellow. Oh, we got 3. Here we go. Come on. In the lead. 1, 2, a 3. Spin it. Oh, he spilled his bucket like a jerk. Stupid Team Green. Spin it. Oh, you got 2 cherries. That's 1, 2. Oh, that's a bird. Well, he already had 0, so no big deal. Back to Yellow. Oh, there it is, Yellow. Good job, Yellow. You get to yell, Hi-Ho Cheerio. I know, so very exciting for a children's game. It's weird. This game can last a very short amount of time, as this one just did. Or, theoretically, how long can this game last? Theoretically, it could. It could. It's unlikely to last forever, but theoretically it could. Which begs the question, approximately how many spins should it take on average to win the game? Approximately how many spins does someone take to win the game? Assuming that this spinner is just, again, completely random, obviously, depending on how much force you give it and depending on what direction you're spinning it and depending on where it starts, that does change certain variations in the randomness. But assuming that all 7 spots have a randomized, 1 to 7 equal chance, how long would it take? I don't know. There are certain guesses that people could have in terms of the number of spins. I don't even know how many spins I took here, like 4 or 5 spins or some junk like that. I don't know. See what happens. But our job today, we are going to run a random simulation in order to attempt to answer that question. How many spins will it take on average? And then we are going to come to a suitable conclusion. So, as I said before, I'm asking for those notebooks to be out and open, as you guys in the class have already done so wonderfully. I'm going to set my son's game aside. Actually, it's my daughter's game now. My son's moved on to other things. I don't know. He wants to play Monopoly, which I'm fearing will turn him into a tyrant. Although I don't know that many 6-year-olds that are not already tyrants. But I digress once again. In my notes, today is the 16th. Oh, happy day. It's interesting. How many months are you guys in school? 10 months? Barely, right? So there's 10 units right there, which means there are 20 half months. We've gone through half the month. Think about that. We've gone through half the month. You know what that means? 5% of the school year is over. Doesn't that creep you out? Anyway, back to me. Let's call this a random simulation of hi, ho, cherry, o. Now, a lot of different things can come under the guise of random simulation, as long as you know precisely what it is that you need to go or need to do. According to what we did last class, we were writing down some of the rules for random simulation. We were writing down some of the procedures that we had to follow. And depending on the real life situation that we're faced with, in this case, Hi-Ho-Cheria, there is a random simulation of 7 spots. So we're going to have to assign some numbers in order to account for this random simulation. Now, what we're going to use in this case, and I'm going to show you how to do this in a little bit, we are going to use in our calculator something called randint 1,7. And I'm going to show you that in a little bit. It's going to be wonderful. It's going to be fantastic. We'll deal with it when the time comes. And let's just say let 1, 2, 3, and 4 be that number of cherries. So, for example, if we do random integer 1,7 and we get on a 4, that means that we are going to take that many cherries off of the tree into our bucket. Oh, happy day. Then we get 1, 2, 3, say, same exact thing. If we end up with a situation where we have 9 cherries in our bucket and we land on a 4, that's just 10. We can't go over 10. We're going to stick with 10 cherries in the bucket. I'm trying to bring up the live stream on my phone right here so I can see people in the chat. So check this out. I got the live stream right there. Look at the live stream on my phone. There's another phone. Look at that. It's like Inception. Oh my gosh. You guys too young for Inception? I don't care. Anyway, back to this. We are going to let 5 and 6 be the bird using 2 cherries. Of course, if you start with 0, you're going to stick with 0. You can't go negative numbers on this thing. So please keep that in mind. And then we are going to let 7 be spilling the bucket back to 0. Doesn't matter where you are. If you're at 9 and you spill your bucket, you're back at 0. Again, when we talked about random simulation last week, we talked about assigning numbers to real life things or events or situations. In this case, the spins on Hi-Ho-Cheria. Now, after there was the assignment of numbers, I believe if you do check your notes, the next part was I needed a stopping point. Well, if one trial is playing the game once, when do I stop? How do I know to stop the trial? According to the rules of Hi-Ho-Cheria, what does that mean? 10 cherries. Yeah. And again, you're not going to have to actually physically move any of the cherries around. You're not going to have to put everything back on the tree or anything like that. But trial ends when 10 cherries are collected. We need to have a stopping point. So you need to identify when your trial is supposed to conclude before you move on to the next trial. Which begs another question. What's the response variable? I have to report something here. The response variable is based on the question that was asked at the beginning. The question that you're seeking to answer. What am I going to report when the trial is over? Ooh. No one wants to say it again? How many spins? Yes, that's the question. That's what the response variable is. That's what has to be reported. That's what comes out of the trial. Whenever you run a random simulation, you have to be able to identify a response variable. The response variable is the output. In our case, the response variable is the number of spins to win. It is the number of spins to win, or the number of spins it took to win, something along those lines. Now, in the end, we are going to come up with a suitable conclusion, but the suitable conclusion that we are going to come up with is going to be taking all of our results and averaging them together. We're going to get into that. But in order to run this random simulation, I need to make sure that your calculators are set up properly. So, ladies and gentlemen, on your graphing calculators on your computer, everybody hit the math button. The math button. The math button, I'm going to zoom in right here. The math button should be right there underneath the alpha button. You should have the same kind of setup that I have, even though I have an 83. If you hit the math button, you should go to this screen right here. Now, I believe yours says like PROB or some junk like that. That's cool. Mine just says PERB, probability. Go over to probability and go down to rand int. I talked about this a little bit last time. I hope I did. I don't remember, but I just want to show this one more time to make certain of it. Now, when I hit rand int, it takes me here. When you hit rand int, do you come to a screen that says lower, upper, all that others? Yes, exactly. If it says lower, upper, that's perfectly fine. Type in 1 for the lower, type in 7 for the upper. Don't type in anything for n. Don't type in anything for n, and just go to paste. If you go to paste, then you'll have the same image that I have up here. If you hit enter, let's just say, hit enter like 3 times. To get the same numbers I do? Yeah, because as we talked about last week, the calculators that you have, the calculator that I have, is pseudo-random. It's not true randomness. It is not true randomness. So, I'm going to have to show you very briefly how to seed your calculator. You can seed your calculator to start somewhere else on this pseudo-random table that the calculator decides to do, which is really nice. So I'm going to suggest that you pick a number. Pick any number you want. Pick your birthday. I'm going to pick today's date for myself. You don't pick today's date. Pick something else. Pick any number you want. It doesn't matter what it is. Then hit the button on the bottom left of your calculator that says STO. It is the button for store. STO with a little arrow key. If you hit that, you can see up on my screen that a little arrow pops up indicating that I am about to store this number somewhere on my calculator. And where it's going to do me the best help is if I store it into the random function. So when I'm here, I'm going to hit math one more time. I'm going to tab over to probability. And I'm going to pick the first option, rand, R-A-N-D. You can store a number into that word random. If you do it, it'll just say the number again like that. And now, if I go back to rand int and type in 1, 7, I guarantee you it'll give me different numbers. Numbers that are different than yours. If they're the same, then that's just coincidence. But yeah, weird. I'll review that one more time when we get a little bit, or when we get started with the simulation. But here's what I want to do. I want to show you what one trial would look like. I want to show you what a trial would look like. Now, here's the thing. Sometimes I'll verbalize this. Don't write this down. Don't write down what I'm about to write down, because you're going to do your own trials. I'm not doing the trials. I'm just going to show you one example. Here's trial 1. Trial 1. So here's what I'm going to do. I'm going to go back to my graphing calculator, and I'm going to run this trial. And then as I'm running this trial, I'm going to record certain pieces of information. So here we go. I'm going to apply hi-ho Cheerio. So rand int 1,7. Let's see. Boom, 5. Oh, crap. That means I lose 2 cherries. But I started with 0, so I'm sticking with 0. Boom, 2. I'm up to 2 cherries. Oh, I got 3 cherries. Notice that right there. I got an extra cherry, so I got 3 total. I'm just keeping track of the number of cherries in my bucket. That's all I'm doing. Boom, 2 more. I got 5 cherries. Good for me. Oh, I'm down to 3. Oh, I'm down to 1. Oh, I'm up to 3. Oh, I'm down to 1. Ah, I'm up to 4. Oh, I'm up to 7. Crap. 1, 0. Again, theoretically, how long can this last? Forever. The other day, I was doing this, a very basic version of this with my prob stat class. And one person took 38 spins in order to get a win. 38 spins. There's no rhyme or reason because it's random numbers. Oh, yeah, 6. Crap. 4. I don't want this trial to last forever. No! 2, 0, 3, 5, 6, 7, 9. Yeah, there's a win. Somebody yell it for me. There he goes. But now again, the question is, my response variable, number of spins. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38. I tied the record. Yesterday and the day before, the record was 38. That's my response variable for my first trial. Here's the thing. You're about to do this, but I promise you, most of yours will not take 38 spins. Most of yours will take somewhere between 5 to 15 spins. Some of you may get upwards of 38. Good for you. You're lucky. But most of you are going to be able to run through these pretty quickly. What I want you to do, I want you to run 5 trials of your own. I want you to run 5 trials of your own. I want you to keep in mind one thing. If you close the calculator and reopen it, the RAM will be cleared, meaning you'll have to reseed the calculator. For those of you in the chat, if you're running through this with us, I'm going to kind of, again, show on the calculator one more time if you need it, but you in the chat, I'm going to ask you to do the same thing on your Chromebooks and report the numbers when you're done, because all I'll need are the 5 numbers from you, the 5 response variables. Let's take some time. Let's knock out this random simulation. Go. So again, for those of you in the chat, just as a reminder, in case you missed it, I'm going to zoom in on the screen right here so you can see it. And this is for anybody who needs to see the seating of the calculator, just in case they messed up with it. But the way that the seating works is that you just pick any number you want. It doesn't matter what that number is. I'm picking today's date. There's an STO button in the bottom left of the calculator above the on button. If you hit STO, it'll give you this little arrow. And then you have to store it in RAND. RAND is found, you can see the bottom of my screen right here. There's the math button. If you hit math and go over to PRB, you can store it into RAND. And it seeds your calculator. And then we can go back to that PRB function for RAND int. Now mine allows me to type in 1,7, but for you, you would put in 1 for the lower, 7 for the upper, and then hit paste, and then keep hitting enter from there. Just as a reminder, you do not have to reseed after each trial. You do not have to reseed after each trial. Just keep going with the hitting enter, because it'll just keep producing random numbers. Anybody get over 30 trials yet? Nice. How many trials are you up to then? Yes! You broke the record. I promise they won't always be like that. What's the lowest number someone's got so far? 4? What's the lowest theoretical number you could get? 3. Yeah, theoretically you could get 3, but 4 is pretty low. Oh, nice. That's randomness. Oh, what am I doing? Actually, I have to scoop the coffee before I pour anything. In a few moments, for those of you that are done, I am going to be collecting your 5 numbers. For those of you who are done. If you're still finishing it, obviously still finish it up. I just want to save a little time and actually collect those that I can now. And for those of you in the chat, if you're doing this simulation, performing this along with us, once you get your 5 numbers, please just type in the 5 numbers into the chat, and I'll include them in our results. There we go. Now, I'm about to show you something in the calculator. It's a little weird. Some of you may or may not have done this before. But I'm going to hit the stat button. In the middle of your calculator, there's a button that says stat, and then the word edit. If you do that, you come to a screen where you can store data in a list. And that is exactly what I'm going to do in a moment. So for those of you that are still finishing up, finish it up. But for those of you who have the 5 numbers for me, just give me a hand in the air, and I'll point, and I'll kind of get your numbers. Go for it. 3. Oh, you got a 3. Nice. Go ahead. Yep. Okay. Who else? Go for it. 4. 14. 11. 7. 25. Okay, go for it. 6. Yep. 32. Okay, go for it. 23. 5, 10, 12. Oop, 12, 10, 17. 4, 12, 16. 7. Say again? 30. Nice. 7, 10, 10, 9, 7. Yes. 13. 21, 36, 24, 12. Good. 12, 10, 13, 11, 35. Nice. Good. 13, 5, 39, 24, 7. Nice. Good. 13, 39, 10, 12, 22. Yes. 6, 9, 7. 79. No, I don't. No, because I'm too scared. I'm just saying I'm scared. Tough luck. That was a joke because it's randomness. That was hilarious. Anyway. Trying to see if anyone in the chat is gonna. There's 7 people in the chat, but I don't know if they want to give me their answers, because if they give me their answers, then they're declaring that they're here today. You know, I don't know who they are. They're gonna make me sad. I'm gonna cry. Did I get everyone in here? Pretty sure I did. Okay, cool. Ah, I did get numbers. Good for you. All right, cool. I'm going to give them a moment to catch up while I'm going to enter whoever's numbers are there, and then we're going to kind of go from there. Let's see what happens. So I got somebody in the chat. Let's see. He got a 3, he got a 40, a 5, a 4, and a 32. Nice. So far we have 70 trials. Now, there's no real telling how many trials you need to do. Sometimes you only need to run like maybe 3 trials if it's just you doing something. But if we have a group of people and you're running like a small number of trials, they can add up to a lot as long as we're all starting from a different random position, which is nice. I'm giving them another moment. Now, what we can do with this data is this, and this is going to be something that you guys are going to do in the future. Under stat, edit, that's where I entered my data. Stat, edit. I entered my data into L1. Oh, I got more results. I got 10, 21, 4, 16, 31. What's nice is that as people give me more results, I can update the list and then get an updated image or set of data, etc. So anyway, if you hit stat and tab over to the word calc, there's a first option that says 1 var stats. That is 1 variable statistics. And I am going to talk about this a little bit more in a little bit. But if you hit 1 variable statistics, it will run an analysis on whatever is typed into L1. Chapow! Now we got some information here. Now remember before I said that most of your results would be between 5 and 15? The reason why I said that is because typically the average of any time I do this, the average is always between 5 and 15. Even with your 79, it still didn't ruin it. His 79 may have pulled the average up ever so slightly, but because your 79 was thrown into the pool with all 70 results that we threw in there, it was kind of diluted almost. And again, I go back to the idea of like soup. If you have like a giant pot of soup and you're like, oh crap, I just dumped a whole thing of garlic in there. Oh, that's going to ruin it. Well, as long as you throw in more like stuff, like, okay, a little more broth, a little bit more vegetables, kind of stir that thing around, it's going to be diluted. And it's not really going to make as much of an impact because of the randomness of the situation. This symbol right here is going to play a major role. This is called X bar. I know, creative name, X bar. This is also going to play a major role moving forward as well. S, some of you may have heard of it before, standard deviation. Does anyone know what standard deviation actually is? Do you know what it is? Okay. I know, someone actually told me that the other day that they're learning that in AP Bio. What is standard deviation? Think of it like this. The average is about 14.76. Some of you got results that were below it. Meaning like, oh, you finished like -5 or -6 from the average. Some people had results above it, like 79. Was it 79 again? Like that was way above. Regardless, everybody had a result that deviated from the average. Deviated from the average, either in the positive direction or the negative direction. The idea of standard deviation is similar. It's not exactly this, but it's very similar to average deviation. Average deviation from the mean. It's like the average deviation from the average. It's very strange. There's a formula for it, which this is not the purpose of today. I'm going to write this down another day. But the idea of sample standard deviation is actually calculated using the deviations squared with an n-1 with a square root on the whole thing, which is so much fun. We're going to get there. We're going to get there. It's going to be fun. For me, not for you. You're probably going to cry a little bit. In fact, I'm kind of counting on that. But the other thing we get from this screen, which is really nice, check this out. It's actually really nice. These should look a little bit more familiar to you. Those should look a little more familiar. The general concept of the 5-number summary, which I'm going to show you some images in a moment. You should know what the median is. By definition, the median is what, the middle data point? So like if we have 70 data points, that's like Well, it should be 35 and 35. It should be like the average of number 35 and 36 or some junk like that. The 50th percentile. What the heck is that? Q1? Ugh. Well, think of it this way. If the median is the 50th percentile, what do you think the Q1 is? Take a wild guess. The what? The first what? Not the first percentile. What? The 25th, because what do you think Q stands for? Quarter or quartile. Yeah, it's the first quartile, meaning this would be the 25th percentile or the 25th percent up the way the data, 50th percent, 75th percent, 100% of the way through. Congratulations. You're not excited. Okay. But that's the way this thing goes. What the heck is that? The what? The population? Kind of. It's the number of trials that we ran. I'm not going to define it as population because I have a definition for population in a little bit, but it's the number of trials that we ran. Technically, and here's the weird part, the very weird part. The population is basically like the maximum or the complete total sum of every game that could be played in the existence of High Hoch area. I'm pretty sure there's an infinite number of ways you could play that game. So unfortunately, we can't really talk about the population in that regard, but I can show you some images. Check this junk out. You're going to learn how to do this in the future when we get to a higher chapter. Look at that junk. You know what that's, guys? You know what that is? It's a box and whisker plot. And that box and whisker plot is kind of ruined by that 79. Now, the interesting thing is, you would look at that 79, which, hold on, let me trace it. You see where it's blinking? You would look at that 79 and you would say, oh, that kind of feels like an outlier. Oh, yeah, it kind of looks like an outlier. There actually is a mathematical definition of what an outlier is. I'm going to give you that definition another class period. But we would actually be able to prove that that thing is definitely an outlier. We would also be able to look at this. What the heck is that? Nope, not a bar graph. You know why? Different type of data. We're going to get into that another day. Again, a bar graph is specifically used for what we call categorical data or qualitative data. Qualitative, quality. This is quantitative data. Quantitative data, it's not a bar graph. It's a histogram. Very big definition there. Very big difference between a histogram and a bar chart. Let me just test something real quick. Let me just see what happens when I remove that 79. No offense to the 79. No offense to the 79. But typically when we run an analysis on data, it is a very good idea to run the analysis both with and without the outlier, and then make note of that in our conclusion. But that's neither here nor there. I just wanted to see what it looked like. Zoom 9 it. Now that looks a little better. Let me see what the box and whisker plot actually looked like. Chapow. Oh, yeah, it does look a bit more with it. Yeah. There's going to be one word I'm going to throw at you right now. It's called skewed. We're skewed. This graph is what we call skewed whenever you see something like this. And again, we're going to get there with graphical displays. I believe this chapter's, I want to say it's 2 and 3. Chapter 2 and 3 in the book, or 3 and 4. I got to double check the chapter numbers. Usually not familiar with that. But that's not where we're at right now. We're on chapters 10, 11, 12. So excited. Now we're going to run an analysis. So I got to come to a conclusion. The conclusion that I need for the time being, I put the 79 out. I got to put the 79 back in. 79, boom. Run the analysis one more time. Chapow. That's the average that I need. So I'm going to come to a conclusion. Zooming out, zooming out, zooming out. Here we go. Conclusion time. And you're going to write this down. Based on our simulation of 75 trials, there was an average of 14.76 spins to win. Now, it's really interesting, again, with the 79 spins. It did not pull the average up all too much. It pulled it up a little bit, but when we removed the 79, the average was somewhere in the 13 range. It pulled it up, but it didn't really pull it up by all that much. It appears that you would have to spin at least 15 times to win. Come on, internet. Silly. When you come to a conclusion about this kind of stuff, you need to answer the question that was posed at the beginning. The answer that was posed at the beginning was, how many spins would it take to win? So number one, fluffy language, based on our simulation. When I say based on our simulation, if there is a simulation or something like that, or based on the data collected, I'm kind of diverting blame. As a statistician, I'm saying, hey, don't blame me, blame the simulation. We ran a simulation of 75 trials. That seems pretty legitimate. But based on the simulation, there was an average of 14.76 spins to win. Okay, cool, fluffy language. Then I say it appears. I'm not saying it is. I'm not saying yes, 15 spins, definitely. I'm not using definitive language whatsoever. I'm saying it appears or it seems. There's evidence to suggest. These are the types of phrasings that you guys have to get used to when it comes to your conclusions. It appears that you would have to spin at least 15 times to win. And I say 15 because clearly you can't have a fraction of a spin. That would be ridiculous. And I did say at least, meaning, again, fluffy language. At least 15, meaning, hey, it could be 15 or more for those of you who got 79 and 39s and whatnot. Reconnect. There we go. Sorry. It keeps crapping out the internet. Whatever. Okay. Such a weird thing. Okay. I need to get you some definitions. Now, as I stated earlier, I am going to be assigning you some stuff out of the textbook soon. I'm going to assign that basically before I leave the building today is what I'm saying. I'm going to assign you something on Google Classroom. And we'll kind of see where it goes from there. But it's going to be something directly out of the textbook. If you have not gotten on the textbook, we need to get on the textbook. We need to be able to access the textbook. I'm actually going to be assigning you some problems, and I'm going to be assigning you to read a certain chapter out of that textbook. But I do need to give you some definitions. So we are jumping a little bit to chapter 11. Sample surveys is what it's called. And I need to give you some definitions. Now, with these definitions, I am going to give you some explanation along the way. Well, we'll see what happens. First, probably the most important, because we talked about it earlier, let's talk about what a population is. Population. A population is an entire group that you're interested in. It's an entire group that you're interested in. Now, what that means is, well, yeah, I mean, I guess if you're talking about population, which people use this phrase all the time, but if you're talking population, people think, oh, yeah, the population of the United States. Well, that's one example. That is one example of a population, but it really depends on what it is that you are interested in. Now, there it is. Okay. I don't know how many people are in this room. Are there 13 people in this room? Yeah, there's 13 people or students in this room, not counting myself. There's 13 students. I had everybody present today. I could say something along the lines of, oh, well, the population that I'm dealing with is my period 1B cohort 1. All of you, and you would be my population. It would make perfect sense in that regards for me to be like, yeah, I could survey each and every single one of you. But that would be called a census. Censuses are mostly a bad idea unless your population is this small. Just makes sense. I can have an entire pot of soup. The entire pot of soup is my population. But then, if I take a spoonful or a bowlful, all of a sudden, I'm taking a sample. A sample is just a portion of that population. It's just a portion of that population. I didn't like this marker. First time. First try, right? Right? For the live stream. I made that shot. See? They're all nodding yes in agreement and like applauding. It's great. Anyway. But a sample is just a portion of that population. Furthermore, you may hear me use the word parameter. You may hear me use the word parameter. Parameters are typically associated with populations. A parameter is a piece of data from the population. It's a piece of data from the population. Now, typically, this is difficult to know. If I wanted to know the average shoe size of every American, I don't know if I'd be able to get every single American and their shoe size. I have no idea if I'd be able to do that. But I could take a sample of like 100 of them, and I can get an average of that, and that could tell me something. But if I could get the population, if I can get the entire population, then that would be a parameter. There are 13 of you in this room. I could measure each of your feet for some reason. That'd be weird. But if I did that, that would be a parameter from the population if you were my population. But unfortunately, you are just 13 students in Barnegat High School, which means if my population is Barnegat High School, you would be a sample. And if I took a piece of data from you, it would be known as a statistic. A parameter, as I said, is typically known as a population parameter. But a statistic is typically known as a sample statistic. Data from the sample. That's typically what this thing comes down to. Very strange. Very weird. Oh, wow, I got like 8 people in the chat right now. Who is showing up for this? Anyway. Furthermore, when you are dealing with parameters, parameter versus statistic, you may have to use different notation. And I'm sorry, you're an AP stat, you're gonna have to use the proper notation. If you're not gonna use the proper notation, then things will be marked wrong. For example, if I'm doing parameter versus statistic and I wanna talk about something about averages, well, if I'm dealing with a parameter, I have to use that symbol. If I'm dealing with a statistic, I have to use that symbol. Y'all know what this is? You ever seen this before in your life? It's the 151st Pokemon. Yeah? You did it! All week, no one's gotten that. Come on, guys. Get your head in your Pokemon game. It's Mew. Mew. Pronounced Mew. I don't even know what to do with that. Mew is a Greek letter. Mew is a Greek letter, as you're going to see a lot of Greek letters rolling around here. This is pronounced X-bar. Very creative, I know. But if you're dealing with a sample statistic, you have to use X-bar. In our calculators, we had X-bar equal to 14.76. That was a sample statistic. The sample was the 75 trials that you all ran. If I had the population parameter, it would be mu. I could also deal with, again, I mentioned standard deviation. Standard deviation, which we're going to get into details a lot later. In the calculator, they use the letter S. That's pronounced S. Just so you know. I didn't know if you knew that. Whereas for standard deviation for a population parameter, which again is very difficult to know, you would have to use this symbol. You know what that symbol is? Say again? Music note? No. It is sigma. It is another Greek letter. Now, typically, you know sigma by a different form. You know sigma by a different form. You know sigma like this. You've seen it like that before? Several people nodding yes. Yes, this is capital sigma. This is lowercase sigma. Greek letters are used all the time for this kind of stuff. It's pretty crazy. They are. Capital sigma is in reference to the sum of. The sum of, when you're adding up a bunch of things. Whereas lowercase sigma, in this case, is typically going to be referred to as the population standard deviation. It's very difficult to know the population standard deviation. Very difficult to know that, which in most real life situations, you're not going to know what it is. But unfortunately, that's what we got. Okay, let's talk about samples now. Because again, it's going to be a little notish heavy today. Let's talk about what is known as an SRS. Some of you may have read about this. An SRS is known as a simple random sample. Or some people say simple random survey. I call it simple random sample, either way. What it really means is each combination of people in the sample, or I'm sorry, each combination of people in the population, what am I saying? I got to be more specific with my words, have an equal chance of being selected. I mean, it could be people, it could be items, it could be objects, it doesn't matter what it is. But each combination of people in the population have an equal chance of being selected. Meaning this, and this is a great year for this. If I went out today to all of the students in Barnegat High School today, September 16th, and I walked up to, a random sample of, 20 of them, some junk like that, and I surveyed them based on some questions. I asked, would that be a simple random sample? I wanted to get the opinion of Barnegat High School students. So I walked around today, September 16th, and I surveyed randomly 20 of them based on whatever random selection I did. Let's say it was a legitimate random selection. Is it what we call a simple random sample? I see several of you nodding no. I'm just going to say it's not. Simply because if I'm going to survey Barnegat High School students, each combination of people should have an equal chance of being selected. If I went out and selected 20 people from across the building, 20 students from across the building, that would not be a simple random sample simply because not everyone's here. Not everyone has an opportunity to be selected. There are people who are virtual right now. There are people who are in cohort 2 right now. If they're not here and they don't have a chance of being selected, I'm sorry, that's not a simple random sample. If I really wanted to be a simple random sample, perhaps I would get an alphabetical listing of every single student in the building and then figure out a way to randomly not in the building, but just enrolled at Barnegat High School. And I figured out a way to randomly select 20 of them, then yes, that would be a simple random sample. Each combination of people in the population have an equal chance of being selected. Very important. Let's talk about a different chance, a different type of sample. Let's call it a systematic sample. A systematic sample, you select subjects by a repeated process repeated process as long as order of list is random. Without an association. I'm going to explain what this is. Without an association with the response sought. Now, what that means is this. I need to select students by some repeated process, as long as the order of the list is random, without an association to the response sought. Meaning, if I decided, okay, there's 13 of you, I'm going to pick every third person walking in the room. I would argue that the order in which you walk in my room is random. I would argue that if I'm going to pick every third person coming in the room for, like, you win a special grand prize or some junk like that, I don't know. The order in which you walk in the room, the association in which you walk in the room, has no regards for that response of getting a prize or being selected to get a prize. But if I'm just saying, every third person, it should be random. It should be, theoretically. Now, again, if I go to the cafeteria, I would say we're not doing cafeteria this year. It's just whatever, stupid. But if the cafeteria was running full force and I decided I'm going to pick every fifth person at the register to survey them on their opinions of the food at Barnegat High School. Ooh, now I have a little bit of an issue. I have an issue. Now, I would say, people buying lunch, it's a random order. I would argue that. Yes, it's a random order in which they buy lunch. And I'm just surveying them on their opinion of Barnegat High School food. But why is that an issue? Why is that an issue?
Because they're the ones that are actually buying lunch, so they have interest in buying it, eating it.
Absolutely. There's an association with the response that I sought, which means that wouldn't be a proper systematic sample. Systematic sample still has to be random. It still has to be random. The randomness that is implied is the order in which people are either walking in or being selected or whatever. I don't know. Has to be random. All these samples have to be random. If they're not going to be random, then there's no point to it. Let's see what else we got. Oh, sweet. I get to talk about, whatchamacallit. I get to talk about Boston cream pie. You guys ever have a real Boston cream pie? Nobody? Oh, man. You haven't lived. Boston cream pie. Like, you've had a Boston cream donut? Okay. For those still shaking their head now, like, I don't know, you're dead to me. But a Boston cream pie is amazing. It's like a Boston cream donut, except better. It has all these different, like, kind of ingredients. It's got the cream. It's got the chocolate. It's got the Boston. I don't know. It's just cream, whatever. Anyway, but there's two types of samples that I'm about to talk about that I'm going to wrap up class with today. Two types of samples that I relate to a Boston cream pie. Now, I want you to imagine something. There's two scenarios about a Boston cream pie that I want you to imagine, and then I want to give you the definitions. Imagine a Boston cream pie sitting in front of me, and then I begin separating things, where it's like, okay, I take the pudding filling or whatever it is, the filling of the Boston cream pie, and I set it aside over here. And I take the chocolate and I set it aside over here. And I take, like, the flaky crust and I set it aside over here. And I take the Boston and I set it aside over here, or whatever that thing is. So I've set it aside to its key components, to its key features. And then I sample a little bit from the filling. I sample a little bit from the chocolate. I sample a little bit from the crust. I sample a little bit from the Boston. And I've done a random sample. I randomly select a little bit from each individual category. That is one example that I'm about to show you in the definition. The second type of sampling that I'm going to show you with Boston cream pies, imagine now, instead of sampling the individual aspects separately, I take a slice of that Boston cream pie. Now, if I take a slice of that Boston cream pie, is it fair to say that slice would have not, I don't care about equal. I don't care if it's equal or not, but would it have a representation of each of those individual things? Would it have a representation of the cream, the chocolate, the crust, the Boston? I would say it would. A nice slice, as long as it's representative of the whole thing. That would be interesting. That would be an idea as to what we're going to be talking about in a moment. And I sample that entire slice. Two types of samples. Let's talk about stratified sample. Stratified. Stratified. The population is split into homogeneous, if I could spell homogeneous today, groups. Then data is collected randomly from each group. And just so you know, these groups that I'm referring to are known as strata. These groups are known as strata. That is the example of taking the Boston cream pie, separating it into its individual components. I take all the cream over here, all the chocolate over here, the flaky crust over here, the Boston over here, and then I randomly sample a little bit from each strata. That is something called stratified sampling. I could do that in the high school. I could say, all right, I'm going to do a stratified sample of Barnegat High School. What's one way I could split up the population of Barnegat High School in order to do a proper stratified sample? What's just one example that I could split them up by? Grade level. Yeah, absolutely. I would argue that the opinions of ninth graders in regards to whatever it is I'm trying to find out, I don't know, college, life, being dumb, freshmen have a much different opinion than that of seniors. I would argue that depending on the grade level that you're in, you might have a different opinion. So maybe it's in my best interest to say, all right, I'm a stratify 9th, 10th, 11th, and 12th. I'm a sample, 10 people randomly from 9th, 10 people randomly from 10th, 10 people randomly from 11th, 10 people randomly from 12th. That would be an example of a stratified sample. I split the population into homogeneous groups, meaning they all have a certain characteristic in common. They're all ninth graders and dumb. I don't know. We don't have any ninth graders in here, right? Did I ever tell you my ninth grade story? No? I taught algebra too. And mostly it's like 10th, 11th, 12th graders, which is what you guys are. And then some kids were making a commotion in the hallway, and stupid freshmen. And I started ripping on freshmen for a little bit. And then other kids in the class are like, yeah, freshmen are dumb. Let's go get them. And I'm like, yeah, that's a great idea. Guys, let's just go out and just start beating up freshmen. And there's this one kid over here who was a freshman, and I knew it. And without skipping a beat, he's like, yeah, guys, let's go get him. I'm like, you sweet, naive fool. Anyway, let's talk about the second type of Boston cream pie. It's called cluster sampling. The population is split into representative clusters. Each cluster should, that's the key word, it should. If it doesn't, then we got a problem. But it should represent the population fairly. It's what we call a representative cluster. It needs to be representative of the population. Now, if I were to say right now, okay, let's split up Barnegat High School by classrooms. So I'm going to then randomly select one of those classrooms, and I get you guys. Now, no offense to anyone here, but do you believe that the people in advanced placement statistics are representative of the population of Barnegat High School? No, not at all. I shouldn't even have said no offense. I was just basically raising your self-esteem. But no, that doesn't work. If I were to say split up by all the classrooms today, right now, you are not representative of Barnegat High School. I'm sorry. Academically, you guys are above and beyond. So you would not be a proper cluster sample. A better way of cluster sampling Barnegat High School, if we did have people in the cafeteria eating lunch, maybe I'd go to one of the three cafeterias, or one of the three lunch periods, I should say, from last year. And then I say, okay, all the students in front of me, you are the cluster. And that could be a good representation. People in there could be a good representation of Barnegat High School. Now, we do have some issues, because if I go to a lunch period where, maybe I'm missing all of the vocational students, or maybe all the seniors went out into the courtyard, I don't know. That's a weird situation. But the cluster should be representative of the population. So if I took a slice, or if I took that Boston cream pie and I sliced it up, and each individual slice represented the whole, and then I randomly selected a slice in order to test it or taste it, then that would be a proper cluster sample. It's going to be great. It's going to be great. Now, ladies and gentlemen, I talked about that. I'm not going to give that now. I'll give that another time. There are other things that I do have to give you, but I'm going to give them to you another time. As I said, I am going to be assigning something on Google Classroom before I leave the building here today. What I wanted to show you before you left, because we do have a couple minutes, I have this box. And this box is filled with hundreds and hundreds and hundreds of multiple choice questions. Now, as of right now, as of September 16th, as far as I know, the AP test is still going to have multiple choice on it. Again, that's as far as I know. Who knows whether that's going to change or not? Come on. Trying to find a good example. But it doesn't want to do it now today for some reason. It doesn't want to give me the problem that I need. Oh, there we go. I think I found them. Nice. There we go. I wanted to show you just an example of a multiple choice question based on some of the information that you may have seen today. Here we go. Here's a good example. Now, again, I'm not going to go into great detail about this because I know that the class period is going to end and I got to get the next live stream going. But this is just one example of a multiple choice question that they may throw at you. Again, one multiple choice out of 40 multiple choice questions. Keep that in mind. But, that's neither here nor there. We're running out of time, and I can't really do this today because it took me forever to find the card. I just wanted to show you that if I do give you multiple choice questions, or if I do kind of an experiment along those lines of doing multiple choice questions, I might do it like this so everyone can see it. Anyway, bell's going to ring in like 3 or 4 seconds, so I'm going to sign off on the live stream. Pay attention to Google Classroom, and we'll see you next time.